Welcome back, guys. It is I got Thursday the 4th or the 3rd, should I say? And we are going to just do a little small session on just review for significant figures, the theory of line leveling. Let me pull up the quick little session here. Get back to this guy. So, back to leveling theory. We used to, the importance of this was back when we started the railroad and roads, transportation. So we'd had surveyors, crew go out, a whole crew, and they just start doing a lot of topographic type of survey. But the most important part of that was all the elevations of the terrain of the United States as they were moving west. So a lot of that has to come to do with the theory or the datum part of it when it comes to understanding the leveling theory. So go up with some of the definitions here. We have what we call the vertical line. We have a line level surface, a line level, a horizontal plane, horizontal line, vertical datum, where date of elevation, geoid, benchmark leveling, vertical control, curve and refraction. So there's a lot of different things, moving parts, and we're just trying to keep it very simple. I'll give you guys the few that we're looking for in this class because we're dealing with plane surveying. We want the um, obviously we want the horizontal plane. We're going to want the vertical datum to know what we're coming off of. We want the elevation. We want to know the benchmark. We want to know the leveling. We want to know vertical control because that's what's going to, give us the standard of what we're looking for when it comes to our differential leveling or our automatic leveling in this class. So quick figure for you guys. And then this is just to kind of put it into perspective here. You have the Earth's surface. The Earth's surface is not, uniform shape. It's a wonky sphere. And so when you guys take a look and you guys review through that, you're looking at just a problematic type of portion. But luckily in plane surveying, we deal with small areas. We don't have to deal with the entire world. We don't have to deal with any type of um, different elevation shifts or units in that or not units significant changes. So let's see. Let's go over a couple of these definitions. So vertical line, just to show you guys, this you got this huge part right here. Vertical line is the line that follows the local direction of gravity as indicated by a plumb line, right? So again, are we really that concerned in plane surveying? Not as much, right? All right, level surface. The curved surface that every point is perpendicular to the local plumb line, the direction in which gravity acts, okay? And then we have level surfaces are known as equal potential surfaces, since for a particular surface, the potential of gravity is equal to every point on the surface. That's our level surface. Moving on to level line here. A line in the level surface, therefore a curved line. A level line is also just used to describe a unit of field consisting of benchmarks and turning points. So that's where you're using your foresights and backsights there. Horizontal plane, a plane perpendicular to the local direction of gravity in plane surveying. So again, one of the things that we care about here in this class. Horizontal line, a line in horizontal plane in a horizontal plane in plane surveying, it is perpendicular to the local vertical. All right. And again, if you guys have the book, the chapter 15, this is all the leveling terms are all on figure 4.1. Again, we're just doing a nice review, so we just get the understanding of the definitions. But yeah, and then vertical datum, any level surface to which elevations are referenced. Elevation, the distance measured along a vertical line from a vertical datum. And then let's see. Oh, sorry, I forgot one key part on the vertical datum. This is the surface that is designed in a zero elevation of zero, right? This level surface is also known as the reference datum, since points using this datum have heights relative to the surface. So again, what are the two surfaces that we use in the United States? Well, the current one is the North American vertical datum of 1988. And then the older one, which is actually still in use, is the North American, gosh, starts with a G. I want to say gravitational datum of 1929 is so NAGD, and then geoid. So now on to geoid, we have a particular level surface that serves as a datum for all elevations and astronomical observations. And then we have the mean sea level, which is not shown here, but part of the definitions. This term is no longer applicable, that's why it's not shown, to benchmark elevations in North American NAVD 88. So again, it was defined as the average height for the surface of seas for all stages of the tide in a 19-year period. Oh no, so it is the National Geodetic Vertical Datum of 1929. NGVD is what it was, not NAGD. So back to our quick session, or back to this right here. So again, just to show you what curvature and refraction is, we have, if you're actually taking, a huge type of measurements, you have to deal with curvature and refraction. So what you would have is your actual line of sight, right, is extended here, this second line here, because of the curvature. And then you have your point of tangency where you would be, or where you would be sitting. You would have a point of tangency running through where the curvature meets a straight line. Then you have your level line, right, as the earth is going, pretending this is that level line here. And then you would have your vertical line through here. All right. So the units that we use are, for one, is this one's in meters, or sorry, this is if you're using English, but you have a meter unit here. This is the formula for it. The other one is if you're going in feet, and then we have the metric one down here, and this is in kilometers here. Methods of determining differences in elevation. So we have differential leveling. We're using backsides and foresides, which you guys are currently doing in the lab. And then we have trigonometry leveling, which you're using total stations, and you're measuring slope distances and zenith angles to compute elevations. So we did a little bit of that in GME 161 with the computation part. We're going to try to get into a little bit more into this term, trigonometry leveling. So equipment used in leveling, and this is for talking about just differential leveling currently. We have the dumpy level, right? This was the old style. That's probably from this, this era here of these pictures. And again, they would use a rod and they would just go from there. We have the automatic levels, what you guys currently use right now. We have what we call geodetic levels. I don't believe we have any of those available for this in our equipment room. And we have digital levels, which are also part. We do have those, and those are the most current type of equipment used in the profession. So this would be, again, an automatic level, kind of looks like the ones that you guys have currently in the equipment room. This is another type of style. No, that's not. I think this is the geodetic level, which again, we don't have. And this is what we have the digital level here. All right. And then we have level rods. Good times. Oh, let me get rid of this thing, make it bigger here. So again, this should look familiar to you guys. You have the level rods here, and then we have, there's different styles, and I'll show you here. I believe this is just the level rod. There's one with so again, this is how we read them, and I think we went over this last time. You got the odds on the top of the bar, and then the evens on the top of the bar, and then the odds on the bottom. And again, so like right here, this is the 5 foot marker right there. So down below is 4 feet, and then whatever to the decimal. So we're right here. and it's at the top of 9, so that's 4.90. And again, we're going to the hundredth. Anything that we measure is always to the hundredth. And this is what we have for the digital. This is just the bar, and this is for the digital levels, right? It just uses this bar. And what you do is usually have a level somewhere on the side of this thing to level it up, plumb it up. And then you just sit on top of the point, hold it. You don't, there's no waving, there's no anything. Sorry. There's nothing like that. You just hold it level, hold it plumb, and then your eye man takes the shot on that rod and gets the reading. And again, these are the hand levels. So you take one of these hand levels like so, or you insert it inside your rod this way from the top, and you would hold that up against your level and make sure it's plumb. All right, parallax. Parallax is one of those things that we have to deal with. We're constantly going to have to deal with when you're looking through the object. And again, parallax is that when you close one eye and it changes the angle of your sight. Maybe so if you close your left eye, you can see everything on the right side, and it kind of shifts everything. That's parallax. It's just again, this is more of a remote sensing or more remote sensing type of theory, but it does have to, you just will have to know that it does affect your readings when you're taking direct elevate, when you're taking those back sights and foresights as you're going through, when you're looking through there. So make sure, if you're having some issues as you're going along your level loop, that you're using both your left and your right and seeing if there's any huge differences in your readings as you're taking foresights and backside shots. Differential leveling, measuring a backside and a foresight to determine the relative vertical balance between points or distance, or not balance, vertical distance between points. And again, you're transferring elevations, right? So if you're coming off a known benchmark, right? So here's your datum down here. Datum is 0, right? And you guys, that's at sea level, and that's determined by in the North American. That's 1988 datum, and we are 820 feet above sea level, right? We're using that datum, and we know we established a benchmark at 820 feet, and then we set up, and we're going to our next point, and we're trying to give it an elevation. So we have to transfer an elevation from here up to here, right? So that transfer again is we already know from a local site. And again, here's a good resource for you guys. All right, let's go GS. Let's just Google it then. Let's go NGS. National Geodetic Survey. All right. Looking for benchmarks and data sheets. It's a great reference here. Hopefully it's seen something. You can click on this interactive maps here. And I mean, look at all these benchmarks. So let's go to Klamath. All right, this is Denver, Colorado, right there. And again, if you're curious about your hometown, this is a great area or this is again, it should have pretty much everything there. And then you have a bunch of different symbology here. So we have a legend right down here, and there we go. We have a horizontal, we have horizontal other, we have vertical adjusted, we have vertical other. And so let's go with looking at these vertical datums down here on South 6th Street. So right here, we have the data sheet, the recovery, the passive, and I want to know, it gives me the, sorry, I'm trying to blink here, description, right? It gives me when it was last found, right? It's still monumented. And then here, this data sheet is going to give me all the information of the benchmark. So clicking on it, we get our information right here, this ortho height, right, is what we're looking for. So this is in metrics, and then this is in feet. And again, all based off that NAVD 88. And here is position by lats and longs, which is another great use. And then we have the other portions of height, right? Dealing with having to do with the geodesy side of the world. All right, and then it gives you the vertical. It's a second class one, so it's really good. It's a really good standard control. So again, NGS, very good. Another awesome site to use for references. All right. So again, you're transferring your elevations. So you start off by reading that. You have your known. You have your setup instrument. You're all leveled up. Again, you're taking that reading, and that reading is giving. That's why we're adding the backside because it's giving us that reading, and so it's going to be that. And so that it becomes an elevation of 828.42 because if you take your backside reading plus your benchmark reading, it gives us the height of instrument from our datum. And now we want to transfer that over to our X point, right? And again, we take that reading and we get a 1.24, and we're going to subtract that from our HI, and it's going to give us that new elevation of 827.22. Does it sound pretty easy? Yeah. But again, this is when you're in the middle of you could be in the middle of a highway and blasting cars going by, and you're trying to take these notes and you're trying to concentrate, you're trying to figure it out. Maybe you got your guy on the radio over there trying to, tell you something while you're trying to take notes down. So again, it's a very simple concept once you get the understanding, once you get the grasp of it. But the physical side of it or the real world side of it can actually, there's many factors that can, cause you to have a relatively easy day become into a nightmare. So just always understand that, things can always go wrong. So you can't just relax and just, think it's going to be a nice, easy day. You got to go in there ready for anything. All right, trigonometry leveling. Again, we went over this last term. I'd like to try this term to actually try to do it in the lab. So we might, bust out the total stations and try a little bit of trig leveling with a couple of these um, benchmarks that we have around campus, starting with Ager. And then with Ager, we just take broad readings from there. And again, we're going to go use the V is slope distance times the cosine of Z, Z being your zenith angle, right? And then H is the slope distance of times the sine of your zenith angle. So again, we have V being here, right? The bump from your horizontal site to the rod reading, and H being here. So again, that becomes that vertical triangle, as you can see by the layout. And then let's find that real quick on 4.7, just to make sure our oh, hang on. It is now. I need to change it. Give me 1 second. Oh, right. Yep, 4.7. There it is. Okay. Yeah, 4.7. And again, we have the difference. H is V, V. Backside. S, yep, slope distance in between C and D, H. Yeah, if horizontals, yeah, H. Yep, just the horizontal distance there. And then V as the elevation difference. Yep. So V is the elevation difference and H is just being the horizontal distance. And to get the elevation of B, you would need the elevation of your A, what you established there. You would need plus the height of your instrument, plus the vertical difference vertical difference there, and then minus your height of where's the little t, where's the little h? Oh, I believe it's here, right? Little r, yeah. So this right here is the same as your little r here. So your difference in rod, right? Your reading there. So that would be your rod reading. This little h. And that would give you the elevation of B in trigonometry leveling. So again, trigonometry leveling, You have all kinds of different ways, or I guess different scenarios when you're doing these things. This is called line levels. So again, you're going to be running through these as you have again little a or hi. You have your a for elevation. You're going to have your zenith angle. You're going to have your h for and your slope distance. You're going to have your vertical differences. But if we're just dealing with the small stuff like plane surveying, this is just the theory. And again, we don't really have to deal with any of this unless it becomes, more than, I would say, anything over 400 feet. It becomes, that where you have to deal with that curvature and refraction type of work. So again, differential leveling, we have level loop, benchmark, turning point benchmark, or sorry, temporary benchmark and turning point. Those are what we use for the definitions for those, right? And so again, when we have sources of error, that is because of the line level and the line level and line of sight. So balancing these can be the tricky part. Yeah. So again, when we have what we call, all right. So on figure 5.7, you can also use the illustrate the importance of balancing sight angle, sight lengths if a collimation error exists in the sight's line of interest. This is why we do the peg test, by the way. This condition exists if after leveling the instrument, its line of sight is not horizontal. For example, suppose in figure 5.7, because the line of sight is systematically directed below horizontal, an error E1 results in the plus sight, but if D1 and D2 are made equal, an error E2 equal to E1 will result on the minus sight and the two will cancel, thus eliminating the effect of instrumental error. On slopes, it may be somewhat difficult to balance lengths of plus and minus sights, but following a zigzag pattern usually works. It should be remembered that the Earth curvature, refraction, collimation errors are systematic and will accumulate in long levelings if care is not taken to balance plus the and minus sight distances. So when we talk about doing these differential levelings, we want to balance the distances. So again, pacing, using the focus, making sure we're relatively close. So we want to always balance those distances. And again, you're always going to deal with different terrain as you're going along. So as long as you are working on balancing the distances, you should be okay in minimizing those errors. So when you cannot balance the distance between the foresight and backsight. So again, when the rod reading is near, right? When it's too close or you're too close to it, it's kind of a perfect example. And it's the same thing as you guys are going along and you say, all right, I'm going to set up just about 20 feet from the rod from my foresight. But in reality, what it should be, you should probably, or let's say your distances between your two readings were, 400 feet and you decided to set up 50 feet from your foresight, when in reality you should have, set up 200 feet. This could be the result in your errors, just to showing you uh, the picture or illustration of it. Oh man, rivers. We haven't done, I've yet to do a river loop myself, but what you would want to do is you would want to set up one on turning point 23. You would want to get there, set it up, take your shots across because again, water levels out. And then you would want to somehow reach the other side and do the exact same scenario and probably try it twice on both sides. So you see if you can balance those angles across the river. It's a very tricky scenario. I have yet to do that one, so I can't really give you much advice on this one. That's going to be a whole hydrographic surveying is a whole different animal too on some of those things. Let's see. So, how precise of a level? Well, again, we're using minimum class 3, right? So when we use this formula, the C equals MK 1.5. That is, where is that level? I just saw it not too long ago. Yeah, it is. C is being the where C is the allowable loop or of the misclosure, right? M is a constant, and K is the total line level in kilometers. So again, this is where you would take your M is, yeah, you take your M as a constant, you take your total line length, and then you could figure out your misclosure and see where you're at there. But again, we use the other standard where we just take the number of setups times our constant of 0.03 or zero point zero 0.02, and that's where we get our class review. All right. So next thing that we want to talk about real quick is just significant figures. So where's my one piece of paper that I've had? Geometric. Oh yeah, this is it. So when talking about significant figure, guys, we have actually there's another different one. Let me go find it real quick. Units. That's the one I wanted. Download this guy real quick. So again, this is all basic review stuff. For a lot of you guys, you've seen this many times, but units are always going to be important. And I'm going to put these guys on canvas for you guys to look at and have. But when it comes to units, this big one, this is the big one right here. This 1 meter equals our US survey feet or international feet. Okay. And let's review that one real quick. Pull it up here on this one right here. So back to my first chapter when I was looking through my notes here. So this is the shift that we care about right here. So in Oregon, the state of Oregon, it uses international feet. I believe all the states around us, so California, Nevada, Idaho, and Washington, maybe actually Washington might be international, but California and Nevada, I think, believe for sure, are in your US survey feet. Why does that make a huge difference in any type of project? Well, um, if we were to take the units that we were to calculate, so let me show you. Let me pull up my Zoom here. Oh no, let's kind of video myself here. So let me grab a quick marker. So in 1983, so the year 1893, you guys see that somewhat? That's backwards. Sorry, guys. Not the right backwards. Huh. Didn't realize it was backwards. Oh man, I have to change that. All right. Well, that might not work. Let's see here. So if I put it like this, would it work? Yeah, year. All right. 18. That's a P. Say 93. That make look sense? No, that's gonna look terrible. It looks gotta look like a P though. 93. Yeah, and that's gotta be backwards. That's what. Don't worry, guys. I'll find a way to get this changed so it doesn't do this because that is not great. So the year 93. Let's see here. Oh, there we go. Okay. now I'm all backwards. Okay, there we go. Fixed it. So year 1983, 18. I keep saying 19. 1893, the USA adopts or adopted the unit to be the standard to be 1 meter equals 39.37 inches. Yeah. Which is exactly, so 1 meter is exactly 39.37 inches. And under this new standard, right, this now becomes decimal or in units or in or per meters. This is 0.348 meters, right? Now, in 1959, year 1959, we get a new standard, and that becomes this one right here that we're looking at on units. Let me see here. I have it. Geostatistics, was it under statistics? No, I guess I didn't have it. Never had it. Okay, well, I'll just write it down. No problem. All right. So we said the new standard in which 1 inch was exactly. So we said 1 inch is exactly 2.54 centimeters. Okay, which that now makes it 1 foot is equal to 0.3048 meters. Okay, so what does that have to do with our world? Well, with our world, this is known as an international foot, right? This has to do as a U.S. survey foot. All right. What does that exactly mean in differences? Well, if we were to differs by, so this is what we say is called, this differs. I'm going to just say by 1 part in 500,000. Or approximately 1 foot per 100 miles. So the thing about it is in plane surveying, we don't have to really deal with that, right? We don't have to really deal with the two international or US survey feet. I just had a job not too long ago where we went to it and I did everything I needed to do. I set up my instrument, I checked into my backsides, checked into another control point, and I'm all good. I'm ready to go. I'm thousands. And then come to find out that uh, my other coworker accidentally had that same job file in US survey feet where I was in international feet, and he was using GPS where I was using total station on the job site because I was laying out stuff, and he was just tying in some irrigation lines for easement stuff. So what that caused is a big shit because he was using GPS where I was using just a total station. It wouldn't matter in a total station setting because if it's, I mean, the whole area probably was, 500 by 600 feet, that little piece in plain surveying. That doesn't change much in that world. But what does change is GNSS or GPS world when you're dealing with two different units and you have to convert those units, and that is dealing with hundreds of miles. So that is where this becomes a big important play is GPS world, not uh, total station plane surveying world. Let's see. So again, that is our review for today. Just again, quick stuff. I was talking to Evan a little bit ago, and he said that you guys, had some growing pains or some character building weather on Tuesday of the first week here. So hopefully this upcoming lab and the rest of the labs for the online campus students, it goes a lot smoother. It looks like it's going to be nice and sunny out there today. But hopefully that is the rest of the weather for the rest of the year. And for my online students, hopefully you guys are dealing with some very nice weather, and again, able to implement some differential leveling as you guys are going along in some projects. We're able just to get your hands on something like that and able to work through them. So, all right, that is it for today. Everybody have a great day, and we will talk to you next time.